Today, I'd like to talk about how two iconic features of the American Southwest, Meteor Crater and the Grand Canyon, may be linked by a single moment in time. A new hypothesis proposes that when the Barringer meteorite struck northern Arizona sometime around 50,000 years ago, the seismic shock from that impact traveled across the Colorado Plateau, triggering a massive cliff collapse deep within the Grand Canyon. The result? A landslide that dammed the Colorado River and created a temporary lake that flooded miles of the canyon upstream. In the summer of 2025, the Geologic Society of America published research led by geologist Carl Karlstrom of the University of New Mexico, working with a team of researchers from across the Southwest, including geologists, dendrochronologists, geochronologists, and planetary scientists. They set out to answer a question that has puzzled Grand Canyon river runners and explorers for decades. Why is there driftwood inside caves that sit more than 100 feet above the modern river? Believe it or not, noticing where driftwood ends up is an important skill on a Grand Canyon river trip. Since 1962, when Glen Canyon Dam was completed, the natural spring floods that once surged through the canyon have been tightly controlled. These floods once reshaped sandbars, redistributed sediment, and left behind clear lines of driftwood along the canyon walls. Today, collecting any wood above that historic flood line is strictly prohibited. It marks some of the highest water levels seen in human memory. But even those largest historic floods only raised the river by 10 to 15 feet above its modern level. So ever since the 1970s, river runners have been asking a much bigger question. How did driftwood end up in places like Stanton's Cave, more than 100 feet above the modern river? At first glance, there are several possible explanations. Maybe a massive Holocene flood once surged through the canyon. Maybe Ice Age climate cycles temporarily raised river levels as terraces formed and eroded away. Maybe lava flows or earlier landslide dams downstream backed up water all the way into Marble Canyon. Each of these ideas has been proposed and studied, but there is one hypothesis that fits both the elevation of the driftwood and its age. A short-lived but enormous landslide dam near Nankoweap Canyon, which flooded the Colorado River, submerging caves like Stanton's beneath a quiet, slackwater lake. And according to this new research, that landslide may have been triggered by something far more dramatic than gravity alone. The shock wave from an iron meteorite slamming into Arizona's limestone bedrock. The work began the old-fashioned way, by heading into the field. Researchers collected 4 pieces of driftwood from 2 separate cave systems high above the Colorado River. 2 of these samples came from Stanton's Cave and were originally collected during early expeditions in the 1970s. The other 2 were gathered from a nearby alcove at River Mile 35.5, where driftwood is embedded in a thin horizontal layer of sand and silt. These sediments tell an important story. Unlike flood debris, which tends to be chaotic and jumbled, the sand and silt in this alcove are carefully layered, deposited by calm, slack water. Even more telling, similar lake sediments occur at multiple heights above the modern river, suggesting the cave was gradually filled as water levels rose and fell during the life of a temporary lake. Once collected, the samples were sent to specialized laboratories in New Zealand and Australia, where they underwent some of the most rigorous dating procedures available. To date the driftwood itself, researchers used radiocarbon dating, but with an unusually careful preparation. The wood was treated using a process known as base acid bleaching, a method designed to isolate pure cellulose from the sample. This step is crucial. Over tens of thousands of years, wood can absorb younger carbon from groundwater, roots, or mineral coatings. Contaminants that can make an ancient sample appear much younger than it truly is. By stripping those contaminants away, scientists ensure that the carbon being measured came only from the trees when it was still alive. To date the surrounding sediment, a completely different clock was used. Infrared stimulated luminescence, or IRSL, measures the last time mineral grains were exposed to sunlight. Tiny imperfections inside minerals like potassium feldspar trap electrons over time. When those grains are buried and shielded from light, the trapped charge builds up. In the lab, infrared light releases that stored energy as a faint glow, a signal that reveals how long the sediment has been buried. Together, these two methods allow scientists to date both the organic material and the mineral sediment independently. Radiocarbon dating tells us when the trees died. IRSL dating tells us when the sand last saw sunlight. If both clocks stop at the same moment, it's a powerful sign that the wood and sediment were deposited together during a single, short-lived event. Remarkably, that's exactly what the researchers found. Radiocarbon dating works by comparing a sample to a calibrated curve, essentially a timeline built from thousands of independent measurements. But like any map, that curve has an edge. These driftwood samples fall right at the outer limits of radiocarbon dating, just beyond where the standard calibration curve is well constrained. To bridge that gap, the researchers turned to an exceptionally detailed climate record preserved in cave formations found in China, which extend further back in time. By smoothly extending that record, and assuming no sudden catastrophic changes in Earth's carbon system at that moment, changes we have no evidence for, they were able to estimate a reliable age. When the Stanton's Cave driftwood was first dated in the 1970s, it appeared to be around 43,000 years old. Already ancient, but still within the limits of early radiocarbon dating. When those samples were reanalyzed using modern techniques, the results shifted dramatically. The wood turned out to be closer to 55,000 years old, nearly 10,000 years older than previously thought. That change doesn't reflect uncertainty in the wood, but progress in the science. Improved chemical cleaning and far more sensitive instruments now allow radiocarbon dating to push closer to its true limits. Just as importantly, driftwood from a completely different cave, tested independently and multiple times, produced the same age. Different samples, different locations, one moment in time. To further test whether the driftwood really came from a single flooding event, the researchers dated the sediments themselves. Thin horizontal layers of sand and silt inside River Mile 35.5 alcove resemble delta deposits forming today where the river enters reservoirs like Lake Mead. Sediments laid down quietly in standing water. Using infrared stimulated luminescence, they dated both a lower and upper layer of this lake sediment. Despite the uncertainties inherent in the method, both ages overlap with roughly 55,000 year age of the driftwood found in the same deposits. Even more compelling, similar sediments and wood appear in caves several miles apart at nearly identical elevations above the river. Different materials, different caves, different dating techniques, all converging on the same moment in time around 55,000 years ago. To understand what might have triggered the creation of an ancient lake within the Grand Canyon, the researchers stepped back and asked a broader question. What else was happening around 55,000 years ago? Large meteor impacts are not just surface events. They send powerful seismic waves through the Earth, capable of triggering ground deformations and landslides far from the impact site. This has been documented at other craters around the world and even during the Tunguska airburst of 1908, which produced a measurable earthquake without leaving a crater at all. The Meteor Crater impact in northern Arizona was caused by a dense iron asteroid traveling at cosmic speeds, releasing energy equivalent to a multi-megaton explosion. Even if only a tiny fraction of that energy was converted into seismic waves, the resulting ground shaking would have been equivalent to a moderate earthquake. At the distance of Nankoweap Canyon, that shaking may have been enough to destabilize already fractured limestone cliffs, triggering a massive landslide that temporarily dammed the Colorado River. While other explanations such as random collapse or local earthquakes cannot be ruled out, the timing is striking. Independent dates from the meteor impact, the driftwood, and the sediments all converge on the same narrow window of time. Taken together, the evidence suggests a remarkable chain of events. A meteor strikes northern Arizona, seismic waves ripple across the Colorado Plateau, cliffs fall deep within the Grand Canyon, and a temporary lake forms, quietly flooding caves that now sit high above the modern river, once submerged in an ancient, long-lost natural reservoir. While more work remains to further refine the exact dating of the meteor impact, it's remarkable to imagine what this landscape may have looked like at the time. A paleolake in the heart of the American Southwest, surrounded by a cooler, greener climate in a world where mammoths and giant ground sloths still roam the region. For a brief moment in time, the Grand Canyon was not just a canyon, but a lake-filled corridor, an ecosystem unlike anything we see today, preserved only in caves and stone. Thank you for joining me today. It's amazing to think about a lake in the heart of Grand Canyon. Today we have modern reservoirs on either end of the Grand Canyon, but this natural reservoir would have been something special to see. I hope you enjoyed this video and appreciate the work done by Carl Karlstrom and these other geologists. I will post a link to their paper below so you can go check it out for yourself. And it's just amazing to think how the Grand Canyon is not just this one moment in time, but a dynamic place that is constantly changing over thousands and millions of years. So if you enjoyed the video, I will see you in the next chapter.